All right, welcome back, folks. For Objective 3, we're talking about rational functions. Here we go. Now, rational functions are functions of the form, we'll say r of x equals the fraction f of x over g of x, where both f of x and g of x are polynomials. Okay, so rational numbers, think fractions. Okay, same thing with our rational functions. They're essentially functions with fractions made of polynomials. For example, if we make a fraction, we could say that 2x plus 1 is a polynomial. We could say x squared minus 9 is a polynomial. Okay, so that's the kind of stuff we're dealing with in this lesson. One other thing quick, just quick vocab word for you, asymptote. That's a line the graph approaches but does not cross. Okay, with rational functions, we'll talk about their asymptotes a bunch just because they'll show up as we go through them. So one of the biggest things we're going to do with rational functions is look at graphing them. And we're going to start off with the simplest rational function we can, just 1 over x. We'll call that the reciprocal function. Okay, we'll start off with a basic reciprocal function and then get into this reciprocal function family where we look at adding transformations, okay, shifting left, right, up, down, stretching, compressing, all that great stuff, just like we've done with a bunch of other parent functions in Algebra 2. Okay, so let's start off by making a table, making a graph of this guy. And I'm going to start off with a 0. Now, when x is 0, our function would be 1 over 0, which is, we'll say, undefined. Okay, we've been saying for years can't divide by 0. If you try to plug that into the calculator, you get an error. So for x equals 0, I'm not going to have a point along my graph. I'll actually have an asymptote. Let's plot some other values. Let's throw a 1 here, and suppose we can extend this line down. Notice I'm leaving a little space here, which we'll fill in a minute. When x is 1, we have for our function 1 over 1, which is just a 1. Okay, so just like with all our parent functions, we have a nice point at 1, 1. When x is 2, we'd have a 1 over 2. If x was 3, we'd have a 1 over 3. And basically what's going to happen on the right side of my graph is the bigger the x gets, the smaller my fraction is going to get. So the graph's going to look something like this. Okay, it's never going to become 0. It's never going to become negative. It's never going to cross that x-axis. We'd say that this x-axis is an asymptote as my graph goes off to the right. Now I did leave a space here for x equals 1/2. Okay, when I have x of 1/2, our function would be 1 over 1/2, which if I divide those fractions, I just have a 2. Okay, and basically the closer I get to the x-axis, such as 1/3, the higher it's going to go. I'd have a 3. 1/4, I'd have a 4. 1/5, I'd have a 5. Okay, so my graph's going to have another asymptote at the y-axis, okay, going up like that. All right, it's going to have a similar shape on the negative side of the graph. When x is -1, we'd have a 1 over -1, which is just a -1. Okay, so we have another nice point to deal with there. When x is -2, we'd have a 1 over -2, which is just -1/2. Same pattern happening on the left side of the graph. The further I get down the x-axis, the closer we're going to get to it. And then same thing with fractional points. If x was a -1/2, we can squeeze it in here. We'd have a 1 over -1/2, which would turn into a -2. Okay, so again, the closer I get to my y-axis, the further down we're going to go. All right, that's my basic reciprocal parent function. We've got the two asymptotes on the x-axis and the y-axis. And then as far as points go, really the only nice ones are at 1 and -1. So those will be the two we plot to kind of give it some shape. From there, we can get into graphing transformations of my reciprocal function. Okay, so graph the reciprocal function, state the domain, range, and asymptotes. All right, so I have this guy. And again, it's just a transformation of my 1 over x. So what I need to think about is how are the +3, the -2, and the 2 going to affect that? Well, just like with any graph we've seen, Anytime I add directly to the x, that's going to shift things left and right. Okay, so that plus 3 is actually going to move this graph left 3. And anytime I subtract or add on the outside of the function after everything's said and done, that's going to shift everything up and down. So this minus 2 is going to move everything down 2. And with this 2 up here, we can think of that as 2 times our 1 over x. Okay, so we're multiplying that function. That's going to be a vertical stretch. We'll just say stretch by 2. Okay, so to graph this, we'll look at doing it in one step. We're going to shift our basic reciprocal function left 3 and down 2. And what I'm going to do is I'm going to take where my asymptotes come together at the origin and move those left 3 and down 2. Okay, that's going to be the new spot that my asymptotes crisscross. See how straight we can draw this guy. And then from there, from my asymptotes, my normal 1 over x function has a point that's right 1 and up 1 here. Okay, like we said though, we stretch this guy by a factor of 2, so what I'll do is I'll go right 1 up 2 for that first point. And same thing from the center of the asymptotes, left 1 down 2. And again, that's really going to be the only nice point that we have. So from there, I'll just fill in the shape. Whoa, that got ugly. And make my graph like that. All right, so we've got our graph, we've got our asymptotes, and this also asks for the domain and range. And for that, what we'll do is we'll just say what x and y can't be. For domain, we'll just say that x is everything except for -3. Okay, -3 would be the spot undefined on my graph. If I try to plug a -3 into this function, we'd be dividing by 0. So x is not equal to -3. And then for the range, we have everything except for -2. So we'll just say y is not equal to -2. All right, there's an example of graphing the reciprocal function, or transformations of it, we should say. There's another shot at this in part B. Why don't you take a minute, pause the video, and go ahead and give that a try before you continue along with the lesson. All right, problem 2 actually works backwards from what we were just doing. All right, in the last problem, we took the equation and made a graph. Here we've got the graph and we want to come up with an equation. So write an equation for the reciprocal function. I could say it's y equals, and we're going to have a fraction with an x on the bottom, plus or minus something here, plus or minus something on the outside. The first thing I want to do is figure out where my asymptotes come together. It looks like there's an asymptote at y equals 2. And x equals 1. Okay, we'll assume those are nice numbers. Okay, so to make those shifts happen, to make everything go up 2, we'll just throw a plus 2 on the outside of the function. And then to go right 1, we'll have a minus 1 on the x. Okay, then from there, we need to think about the stretch factor. Now, normally, my graph has a point that's right 1, up 1 from the center of the asymptotes. This one has one that's right 1 and down 1, which is how I know things are flipped upside down, so we'll just throw a -1 on top there. All right, so that'd be the approach, kind of the opposite approach we do when we want to come up with an equation given a graph. The next thing we're going to do is take a look at graphing rational functions in general, or we could say just uglier rational functions, where the polynomials on top and bottom are more complicated than just a 1 and an x. Okay, so what I have here is a rational function, both in expanded and factored form, where I factored my numerator and denominator, along with a picture of what that graph looks like. And we're going to talk about for a few minutes is how these two forms here, okay, lead to this picture we ended up with. First thing we're looking at finding are the vertical asymptotes. Okay, the asymptotes that run up and down on this graph. And I'm going to say they occur at the real zeros of the denominator that aren't also zeros in the numerator. Okay, zeros of the denominator, so in factored form, if I find my zeros such as -1 and +2, I know if I plug those in, I'd be dividing by 0. We can't divide by 0, that's why the graph displays this behavior, why it has a hole, okay, or an asymptote at those zeros. Next thing we'll talk about are the horizontal asymptotes of rational functions. And this will probably be the one tricky part just because there's a few different cases to work with. Okay, so we'll say for a rational function of the form f of x over g of x, where here we'll just expand those polynomials on top and bottom out, like we have in the first case. Just like with polynomials, we're only going to look at the first terms of the numerator and denominator. Those will be the ones that really take this function over as we move to the left and right. And we're going to think of it as a tug of war, okay, between these two terms and their degrees. Okay, if n is less than m, okay, so as in the top degree is less than the bottom degree, the asymptote is y equals 0. Okay, so that'll be the case where the bottom wins the tug of war, and our graph is going to get pulled down to the y-axis, just like with our, x-axis, just like with our reciprocal function. Now, if n is equal to m, so if they're equal, we'll say that the asymptote is equal to y equals a sub n over b sub n. So that'll be this case here where I have an equal degree between numerator and denominator. In that case, we'll just make a fraction out of the coefficients, the 2 and the 1 here. That's why we see this graph with the asymptote at y equals 2, okay, because we have that equal degree. Final case is going to be when n is greater than m, okay, when the numerator wins the tug of war. In that case, we'll have the asymptote y equals q of x, where f of x is equal to g of x times q of x plus r of x. In other words, divide f by g, and the quotient we end up with will be what we call the slant asymptote, okay, the line that things follow. Okay, a lot going on here. We'll go through an example of each of these before we set you free to practice here today. All right, we also want to talk about x-intercepts. Now, those are going to be the real zeros of the numerator. Okay, if I have 0 on top of my fraction, the whole thing is 0. Okay, so the reason I have zeros or x-intercepts of 0 and 3 is because 0 and 3 would be the zeros of my numerator. And then last thing we have the y-intercept. That's just going to be y equals f of 0. Okay, because the y-intercept is going to happen where x is equal to 0 here. So basically plug in zeros for all my x's, I'd end up with a 0 on the top. That's why this graph crosses the y-axis as 0 as well. All right, let's go ahead and start graphing some rational functions. Now my first step is going to be to factor the numerator and denominator. Okay, because some of the stuff we figure out is going to be in expanded form like this, but most of it's going to be in factored form. Numerator, x minus 3. Can't factor that, we'll just leave that as is. Denominator, though, I can factor this as an x, let's see here, minus 4 times x plus 2. And then once I'm in factored form, I can start figuring out those 4 pieces of information, the vertical asymptotes, horizontal asymptotes, x and y intercepts. Let's start off with the vertical asymptotes. We'll say VA. Now we said that's going to be equal to the real zeros of the denominator. So in this case, we'd have a 0 at 4. Because if I plugged a 4 into this denominator, this first factor would be 4 minus 4 is 0. Okay, times, I suppose, 6. Well, 0 times anything is 0. That's why we have a vertical asymptote at 4. And then also for that second factor, negative 2. Okay, so I can draw those in vertical asymptotes at -2 and 1, 2, 3, 4, and 4. All right, next up, horizontal asymptotes. We could say HA. For that, we need to look at the degrees on our function. Now here we have a first degree divided by a second degree. So as far as that tug of war goes, the bottom wins. That's going to be my first case where the asymptote's just y equals 0. Okay, I don't need to draw this in, but just to remember, as we go through connecting the dots, I'll put that asymptote along the x-axis here. All right, next up we have the x-intercepts. We said that was the real zeros of the numerator. Okay, it looks like I'll have one of them here, just an x equals 3. Okay, so we can draw a point along the x-axis at 3. And then for the y-intercepts, we said that happens at f of 0, which if I fill in zeros for everything here, I'd have a 0 minus 3, all right, over 0 squared minus 2 times 0 minus 8. Well, if I cancel out all my zeros here, I end up with a -3 over -8, in other words, 3/8. Okay, you can probably just do that in your head, ignoring all the x's. Okay, so that's going to be my y-intercept. Okay, not a nice number, but we'll say here. All right, then from there I can connect my dots. I can't cross the vertical asymptotes, so I know the middle of the graph is going to have to look something like this. Notice I did cross my horizontal asymptote for a 0 in this case. That is okay. And then the last thing I'm going to need to do is figure out what the graph looks like on the right side and left side. For some problems, you're going to be able to just connect the dots. In this case, we're not sure. So I'm just going to plot another point. I'll put one at x equals 5. Okay, f of 5 would be a 5 minus 3 over 5 squared minus 2 times 5 minus 8. Okay, so that's going to give me a 2 over, let's see here, 25 minus 10 would be 15, minus 8 would be a 7, 2/7. Okay, so I can plot a point about a 2/7, and it's really not important what the actual value is. We just want to know if it's above or below that x-axis. In this case, it's above. So kind of like with our reciprocal function, we can just draw the rest of the graph in following those asymptotes. Okay, we want to do the same thing on the left side. We can plot a point at -3. All right, f of -3 is going to be equal to -3 minus 3, okay, over -3 squared minus 2 times -3 minus 8. And that'll give us a -6 on top over a 9, let's see here, plus 6. So 15 minus 8 would be 7. So here we have a point at -6/7, so about there. Again, it's not super important what that exact value is. We want to know if it's positive or negative, just so we can figure out if that graph goes above or below the x-axis. All right, so there's an example of graphing an ugly rational function with the vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts, and then plotting some additional points if we need to. Let's take a look at a few more examples here. Okay, step 1, factor numerator and denominator. Okay, in this case, it looks like I can pull a 2 out of the numerator just to make life easier. So some scratch work, I'd have a 2 times x squared minus 2x minus 8. And once I do that, it looks like I get the same factorings I had in my denominator earlier. Okay, Okay, x minus 4 times x minus, plus 2. And the same thing, factor my denominator. Looks like this is our difference of squares pattern. X minus 2 times x plus 2. Now notice in this case we have a common factor, x plus 2 on top and bottom. So I'm going to cancel those out. Those aren't going to affect my vertical asymptotes or zeros. Okay, that is actually making a hole in the graph at that point. We'll show you what that looks like in a second. Okay, so moving on then, vertical asymptotes, VA, we said that was the zeros of the denominator that aren't also zeros in the numerator. So in this case, we just have one at x equals 2. All right, horizontal asymptotes, HA. Okay, this is our case where the numerator and denominator have the same degree, okay, both squared. So as far as our tug of war goes, it's going to balance out. If we think of this as a 1x squared on the bottom, our horizontal asymptote is just going to be y equals a 2 over 1. In other words, just a 2. All right, we also have x-intercepts. That's going to occur at the real zeros of the numerator that aren't also zeros of the denominator. Okay, so we won't include it if they cancel out. That'll be an x equals 4 for this one. So we can plot that point. And then y-intercepts, again, that's going to be at f of 0, which for this one, if I fill in zeros for all the x's, I'm going to end up with a negative 16 over negative 4 left over, which turns into just a positive 4. So we'll plot a 4 along the y-axis. Okay, so not a lot to go with, but I'm going to say from here we can fill in the graph. If I know I can't cross these asymptotes, the right side of the graph is going to have to look something like this, and the left side will look something like this. All right, then last thing, let's take care of these factors we canceled, because our graph's going to take on the shape of just what we're left with here. But in actuality, the function we have actually has these factors in. Okay, so when things cancel, what we'll have is a hole at x equals negative 2. So what I'll do for that is I'll just draw a kind of hole in there. I'm not even going to worry about erasing it. That's just something to show that this graph is undefined at negative 2. If I plugged it into either of my denominators here, I would get a 0. Okay, it continues like it goes through there, but it's undefined at that point. All right, let's take a look at one more example. Once again, factor numerator and denominator. Numerator looks like it's going to turn into an x minus 2 times an x minus 1. Denominator we'll just leave as x plus 1. Okay, once again, vertical asymptotes. Those are the zeros of my denominator. So in this case, I'd have an x equals negative 1. Okay, as far as horizontal asymptotes go, we'll compare the degrees of numerator and denominator. So if we have a 2 over a 1, this is going to be the case where the numerator wins the tug of war, and our graph's going to be pulled up into what's called a slant asymptote. Okay, to figure that out, so we'll say HA, what I need to do is divide these two fractions. So we'll go x plus 1 divided into x squared minus 3x plus 2. Okay, so a little long division. X goes into x squared x times x is x squared, and x times 1 is just an x. All right, and we will subtract those. X squareds will cancel, and negative 3x minus the x will be a minus 4x. And we'll pull down the 2. All right, going through that pattern one more time. X goes into negative 4x, negative 4 times. And actually, at this point, I could quit my division. We'll finish it off here quick. Negative 4 times x plus 1 is going to be a negative 4x minus 4. Okay, subtract that. We end up with a negative 4x is canceling. Okay, 2 minus negative 4 would be a 6. That's my remainder. Really what I'm looking for here is my slant. For my slant asymptotes is x minus 4. Okay, so I could say I have a slant at y equals x minus 4. If we think in terms of y equals mx plus b, that's going to be aligned with a y-intercept of negative 4 and a slope of just 1, so up 1 over 1. So we'll go down to the y-axis at negative 4 right here, and then just continue up 1 over 1 through the coordinate system. Okay, so rather than a horizontal asymptote, we'll follow that slant asymptote as we go through here. All right, we also want x-intercepts. That's going to be the zeros of my numerator, which I'd have a 2 and a 1. We also want our y-intercept, which is again just f of 0. Okay, plugging zeros in for my x's, I'd end up with a 2 over 1 here as well, so a 2. And then again from there I can connect my dots. If I follow the asymptotes on the right side, I know my graph's going to look something like this. And then the left side, there's really not any information here. But since I know I don't have an x-axis, I know my graph can't be above the slant asymptote. It's got to be down below it, like this here. Now, if I wanted to confirm that, I could plot a point at x equals negative 2, but just based on what I know it can't be, I know I can put my chunk of my graph right there. All right, so that's it for the graphing portion of the lesson. A lot going on there. Really, once you start doing a few of these problems on your own, you're going to see kind of how they all work together. Really turns out where they're not too bad. All right, the next thing we're going to take a look at is simplifying rational expressions. Okay, so problem 4, simplify the rational expression, state any restrictions on the variables. Okay, so we have a rational expression here, and kind of like we did with graphing, I want to see if I can make this look simpler, if I can cancel anything out. And the first step I'm going to do is factor the numerator and denominator. Okay, numerator, x squared minus 4. That's my difference of squares pattern. I can factor that into an x minus 2 and an x plus 2. All right, and that's going to work because with the minus 2, positive 2, the 2x and the negative 2x will cancel out. Denominator I want to look to factor as well. Trinomial, and it looks like I can factor this as an x plus 7 times an x minus 2. All right, we're going to rip through the factoring part pretty quick here. If you need to spend more time with your factoring, that's fine. Okay, but at this point in the course, we know that's something you know how to do. We're going to focus more on the stuff we don't know how to do here, the new parts. Okay, so factor and then simplify. Basically what I can do is if I have a factor that's in common on the top and bottom, I can just cancel those out. Okay, 2x, or x minus 2 divided by x minus 2 is just a 1. Those will go away. And what I'm left with then is just an x plus 2 on top over an x plus 7 on the bottom. Okay, I'd say that's this rational expression simplified. All right, other part of the question says state any restrictions on the variables. That's going to be basically what our x values can't be. And like we've said before, you can't divide by 0, meaning that I can't have a negative 7 for this factor. Also can't have a positive 2. Even though we're looking at the simpler expression where a positive 2 is fine, what I'm really talking about this original expression, so we want to look for restrictions prior to canceling things out. Okay, so my restrictions here would say is x is not equal to negative 7 and 2. Next thing we're going to look at is multiplying rational expressions. Okay, so here I have one rational expression, okay, times another one. So multiply and simplify. Now, multiplying my rational expressions are just going to come down to writing the factors next to each other. Remember, when you multiply fractions, you just multiply straight across the top and straight across the bottom. Okay, so first thing we'll do is we'll factor once again. X squared minus 9, that's my difference of squares pattern. Okay, x minus 3 times an x plus 3. Okay, times this trinomial here, x squared plus 7x plus 10. Looks like I can factor that as an x plus 2 and an x plus 5. All right, then same idea on the bottom. Okay, my first denominator, two terms. Notice both of them have an x in it, so I can pull that out. I can write this as an x times x plus 5. And then second denominator, looks like I could factor that as an x minus 3 times an x plus 2. All right, so we factored things, and again, multiplying just comes down to writing those factors next to each other. Okay, now for the fun part, just like we did a minute ago, I can cancel any factors that show up on top and bottom. There's an x minus 3 on top and bottom that'll cancel. There's an x plus 5 on top and bottom that'll cancel, along with an x plus 2. So what I'm left with then is x plus 3 by itself on top. And then on the bottom, we just have the x. All right, so there's my simplified rational expression after the multiplication. Once again, we want to state any restrictions on the variables. Okay, so we'll say x can't be equal to a 0, okay, for that lone x by itself. But then once again, also I want to look at the pre-simplified form to check for restrictions. I also can't have a negative 5, a positive 3, or a negative 2. Okay, those would all cause division by 0. Okay, so we'll include those in our restrictions. Terrible looking circle. Whoops. Last problem we're going to look at is dividing rational expressions. Okay, so simplify the rational expression. We'll divide and then simplify. Okay, now once again, look to factor if possible. Now here I don't have any binomials or any multi-termed factors. Okay, so there's nothing to factor here. What we'll do for division is, remember, dividing fractions comes down to turning it into multiplication. We'll leave the first fraction right side up, 2x over 3y squared. And then we'll multiply that by the second fraction flipped upside down, the reciprocal of the second fraction. Okay, so multiplication of fractions is just, division of fractions is just multiplying by the reciprocal. And then from there, multiplying just comes down to writing those factors next to each other. Okay, 2x times y to the third is just 2x y to the third. For my denominator, I suppose I can multiply the 3 and the 15 together, the 3 and the 5 together to give me a 15. And then we can say y squared x squared. And then like we did a few minutes ago, we'll cancel out factors that are the same on top and bottom. Okay, the x on top will cancel out with one of the x's on bottom, leaving with just a single x. And then the y squared on bottom will take care of the y to the third, leaving me with a y to the 1. So my final answer then is 2y over 15x. All right, remember when we're combining expressions with exponents, the trick is we're subtracting those exponents. So if I have a 1 and I subtract 2, they'll give me a -1. Okay, negative exponents will go on the bottom. Okay, so there's my simplified form. Once again, I want to look at restrictions. For this, I can't have x equal to 0 because that would cause division by 0. And also y is not equal to 0 as well. So that's it for our review of rational functions and rational expressions. Okay, start getting to work on the practice. We'll be here to help if you need it.